So today we're going to focus on atomic structure. The aim will be to finish at 7 o'clock still. Luckily, atomic structure isn't as big a topic, so there isn't as much to kind of talk about. So the aim hopefully will be to do some atomic structure, to do some questions, and then hopefully we get some time to attempt some exam style questions at the end. Since this one isn't as long a chapter, it's still a fundamental part of chemistry, but isn't as long. Give it a couple of minutes and a couple of seconds, really, and I'll get started. Right, cool. Right, so we're going to start by talking about fundamental particles. So what is an element? What are the constituents of an atom? What is the relative charge and relative masses of substances within an atom? So we need to first start by appreciating that knowledge and understanding of atomic structure has evolved over time. So we started with understanding about elements. So elements are basically groups of one type of atom. For example, oxygen, the element is only made up of oxygen atoms. Now, elements, we thought that that was kind of it. We were like, okay, you know what? Elements kind of represent all that there is that we know. And then scientists kind of went further and discovered subatomic particles. So subatomic particles are the constituent building blocks of elements. Now, there are things smaller than subatomic particles, which we're not going to talk about because it's not part of the chemistry specification. But these are the smallest things that we're working with. And these are protons, neutrons, and electrons. So what is the charge on an element? Net charge. An element should be neutral, right? An element should be neutral. And that is to do with the relative numbers of subatomic particles within the atom of the element. So atoms consist of protons, electrons, and neutrons. A proton, if you imagine it, P for positive, has a relative charge of +1 and a relative mass of 1. Because remember, although it probably doesn't have a mass of 1 gram, relative to everything else, it has quite a large mass. Neutron, if you imagine neut, so like neutral, is a relative charge of 0 and a relative mass of 1. And electrons are used to balance out the positive charge of the proton. So have a relative charge of -1. But their relative mass is 1/1820. Or approximately 1/2000, 1/2000. So electrons are much more smaller. The recordings that will be uploaded to YouTube, so you won't be sent the recordings, but the recordings will be uploaded to YouTube for you to access after the lesson. The slides won't be accessible, but what we can do is you can go through them on the YouTube link. In the textbook, it says that the charge of a proton is 1.00843. Oddly specific. You won't need that specific or that level of knowledge for a chemistry exam. Generally, at an A-level standard, maybe post A-level, you might be expected to. But 1/1820 is the relative mass of an electron. Yeah. So an electron is much more smaller, which means that an electron is very electronegative dense in the sense that its negativity is incredibly densely compacted within the subatomic particle, whereas a proton's charge is quite spread out within that particle. So as we can see, we've got all of these subatomic particles and their relative masses and relative charges. The nucleus of the atom is the structure that consists of protons and neutrons. The electrons orbit in electronic clouds around the nucleus, and they're held in place by an electrostatic force of attraction between the nucleus and the electrons, because the nucleus is quite densely positive and the electrons are negatively charged, so they're attracted inwards towards the nucleus. And we'll talk a lot more when we talk about bonding and structure about how that affects the bonding of an atom. Electrons spin around in orbitals around the nucleus because they're orbiting. The electrons can have different energy levels depending on how close or how far the electrons are to the nucleus. Sorry, could everyone please ensure that they're on mute? Okay, so that's kind of it for fundamental particles. Does anyone have any questions about that? No? No? Everyone okay? Fine. Okay, mass number and isotopes. So mass number so the atomic number is the number of protons in the nucleus. Each element has its own atomic number, which is characteristic of the particular element that we are showing. The mass number is the total number of protons and electrons in the nucleus. Electrons have negligible mass, so they're not included in the mass number. As you can see, mass number, electron number, and the element symbol. So your mass number is on top, or the bigger number, your atomic number, the smaller number. And in the periodic table, atoms are arranged in the order of increasing atomic number. So simple calculations you should be aware of. So mass number is the number of protons plus the number of neutrons. Atomic number is the number of protons. Number of neutrons is the mass number minus the atomic number. And the number of electrons equals the number of protons in an atom. So a particle with no electric charge is going to, if it gains an electron, is going to become a cation. The way I think about that is kind of like cats, and cats are quite cool, and so I feel positive about them. And the other loss of electron forms an anion, and the way I remember that is anion sounds like onion, and onions make you cry when you cut them. So that's a good way of remembering the difference between cation and anion. It's really important to remember that when, yeah, cations are always positive. That's good. No, it's really important to remember that, because when you're talking about electrolysis, you'll often be asked about the cathode and the anode. So remember that the cations go towards the cathode and the anions go towards the anode. But that doesn't mean that the cathode is a positively charged electrode. A cathode is negatively charged because it attracts the cations, which are positively charged. So it's an important distinction to make, because it's the opposite when it comes to the electrodes in electrolysis. Ions are formed from when atoms have or lose electrons, and electrons are transferred between atoms. The types of ions, so cation, anion. Cation is a positive ion formed when an atom has lost electrons. It contains less electrons than protons. And an anion is a negative ion formed when an atom has gained electrons. It contains more electrons than protons. And remember that because one of these ions will be positively charged and one of these ions will be negatively charged, they're going to be attracted to each other because opposite charges attract, and the opposite charges will be attracted to each other, and that's going to create the electrostatic attraction required to form an ionic bond, which holds a structure together in bonding and structure. So you can see NaCl, for example. So the cation, sodium, Na+, and the anion, Cl, Cl-, and they're attracted to each other to form NaCl as a compound. For ions, then remember that the number of electrons doesn't equal the number of protons, but the atomic and mass numbers should stay the same because it's only about the transfer of electrons through the structure. So for calcium, is this for A-level or for GCSE? So this is basic A-level content plus it's also used in GCSE. So it's basically a bit of a recap of GCSE. We are going to go into more complex stuff in future lessons. So calcium has an atomic number of 20 and a mass number of 40.1. That indicates that it has 20 protons, 20 electrons in the atomic form, and it has around 20 neutrons. Can anyone tell me why? Can anyone tell me why the mass number for calcium is a decimal? Because surely you can only have a full number of neutrons and protons. Yeah, exactly. It's isotopes. So it's the mean mass of all of the relative abundances of all of the isotopes. So it is slightly more difficult. For calcium 2+, the atomic number and the mass number don't change. So it's still 20 and around 20 neutrons, but the electrons will change. So it will have 18 electrons because it's lost 2 electrons to form the 2+ ion. The atomic number of proton is always the same as the number, it's always the same between ions. As soon as the proton number changes, the atom is no longer of the same element. Isotopes, good question, Evan. Isotopes, where we're about to come onto it, are atoms of the same element with a different number of neutrons. Now, this is really important because isotopes will usually have similar chemical and bonding properties. And the reason is because isotopes, the chemical and physical bonding properties are determined by the number of electrons, not determined by the number of neutrons, which means although they'll have different mass numbers, they'll have the same atomic number and very similar chemical and physical bonding. So isotopes of hydrogen include protium, deuterium, and tritium, H1, H2, and H3. And you can see that all of them consists of different numbers. So protium consists of no neutrons, just one proton. Deuterium consists of 1 proton and 1 neutron, and tritium, 1 proton, 2 neutrons. So the proton number will always remain the same, but the number of neutrons will change. So the physical properties like density, boiling point, and melting point can change between isotopes. The reason is because the heavier an item is, the more mass that it takes up, the harder it is the longer it's going to take to burn, the more dense it's going to be, and the higher the melting point is going to be. But the chemical properties, so its ability to form reactions and its ability to react with other structures, is going to stay the same because that's determined by the number and arrangement of electrons, which doesn't change. So as you can see, an example of two isotopes, Cl35 and Cl37. They both have an atomic number of 17, but different mass numbers due to a different number of neutrons. Okay, so we're about to get onto mass spectrometry. Before we can do that, I want to see if I can do if there's a practice question available for it. There might not be. Okay, so mass spectrometers are instruments where we measure the relative molecular mass, relative atomic mass, and relative isotopic abundance. AQA and other specs tend to focus on the time of flight mass spectrometer. This spectrometer differentiates molecules based on the time taken for them to travel through the machine. So we're going to talk about the 4 processes of a molecule passing through a time of flight spectrometer. So the first process is ionization. So a sample is vaporized into a gas form and is put into a mass spectrometer. When it's put into a mass spectrometer, it is immediately hit with an electron beam. This electron beam is going to make the mass spectrometer, is going to make all of the gas in the mass spectrometer immediately an ion. It's going to make it an ion. And this ionization can happen in 2 ways. Either through electrospray ionization, which is where you apply a voltage, causing each particle to gain a proton, which then means that the sample of gas will gain 1 in mass, which means that when you're calculating at the end, you'll have to take 1 out of their mass. So you have to take 1 off their mass. But this then converts the sample into a gas made of positive ions, or electron impact ionization, which is where an electron gun is used to fire high energy electrons at the particles. And if you imagine that there's a particle with protons, neutrons, and electrons in a circle, firing a particle, firing an electron at this, what it's going to do is it's not going to change the mass by adding a proton. It's going to change the charge by repelling an electron away from the atom. So what it does is it repels that electron away. And that then creates, again, positive +1 ions, but not +1 ions with a changed mass. So it's really important to note that. If they're using electrospray ionization, they gain 1 in mass. If they use electron impact ionization, they don't gain 1 in mass. Does that make sense? Everyone kind of okay with that? Cool. Then, now these are positively charged ions. What's going to happen is they're going to create an electric field, which is an electric current around the sides of this structure. And this electric current is basically going to cause all of the ions to move through at different speeds, because the greater the mass of something is, the slower it's going to be able to reach its acceleration point. So the greater the mass, the longer it's going to take for that structure to pass through the time of flight spectrometer. So although they will all have the same kinetic energy, if you remember that kinetic energy from your GCSE in physics is equal to a half mv squared. So if all of these will have the same kinetic energy, but they're going to have a different mass, something is going to have an increased mass, then its velocity is going to be reduced, which means its actual speed traveling through the structure is going to be lower. And once that happens, then the time taken for it to reach the plate where it then gets analyzed is also going to be reduced, which means that it then will arrive at a different point, and then it will be detected by the detection plate at a different point. So light ions are going to bend too much, heavy ions will bend a little bit more, and then the ions will be picked up by the detection plate, and they're going to be generated, and you're going to generate a mass spectrum. So I've got a question here from Imran. Question: if isotopes are in a line and traveling at different speeds, surely they would collide with each other, distort the time, velocity, and acceleration measurement. They're not in a line. That's for diagrammatic purposes. But remember, they're bouncing through the line, which although will distort, it will distort by the same relative. The theory goes, anyway, that they'll be distorted by the same amount. So it wouldn't then affect how overall would not have an effect. Does mass spectrometry apply in OCRA? Yes, it does. I did OCRA, and mass spectrometry does come up in OCRA. And also the entire process takes place in a vacuum. Yeah, so not oxygen molecules too. They can only collide with the walls of the mass spectrometer. From my experience, do I find many exam questions relating to this piece of equipment? Not a lot. It's not a common thing to come up in the exam, but the idea is it will come up as a 3 marker if it does, so you would want to be prepped for it. This is the hardest thing they can ask you from this unit of atomic structure. So you should feel relatively secure about it before you go into your exams. And it does tend to come up in AS exams because it is one of the harder topics in AS. They don't tend to put it in A2 exams because, again, there are harder topics you'll cover in A2, which again, we'll do in the second half of the year. Does that all make sense? Any questions about mass spectrometry? I'm leaving answered questions here because I want to give you some time to also write down this process. Thanks for letting me know. Nope, no questions. Is this whole hour for AS? I can answer A2 questions, but again, be wary that a lot of the people in this class will probably be AS students. So you might want to be wary about it. Sometimes time of flight calculations do come up in A2 exams. They didn't come up in my spec, but other specs they might come up in. Any other questions? Yep. Cool. So yeah, a mass spectrum shows the data from the spectrometer. The y-axis will show the relative abundance of ions given as a percentage, and the x-axis will show the mass charge ratio, MZ. Remember, the charge is normally +1, so the mass charge ratio is usually just the mass, because the charge is always the same. Because the mass charge ratio is decided as the mass over the charge. So that even though, because the charge is always +1, the ratio is normally just the mass. The type of ionization will change the spectrum slightly, as we learned there were two ways. So remember, if an electron impact ionization is used, the MZ ratio is equal to the relative mass of the isotope. But if an electrospray ionization is used, then the MZ ratio is 1 unit greater than the relative mass because a proton is added, hence the mass number will increase. Yes, this is year 12 content. So each line represents a different particle at different mass, and then the relative abundance will show you the relative abundance of those particular isotopes. So remember, if you're studying an element, each peak will represent a different isotope of chlorine. So you might see a peak at 35 and 37 for the two isotopes of chlorine, Cl35 and Cl37. I did OCRA. Chlorine has two isotopes, Cl35, Cl37. Okay. So some elements tend to only have one stable isotope. One example of this is uranium. Uranium-235, rapidly unstable, can decompose very quickly, so very unlikely to be seen on an isotopic abundance. But, so the height of each peak gives the relative abundance. The higher the peak, the more abundant that isotope is relative to the other isotopes. So this is also a way, a lot of scientists measure half-life using this as an instant impact of half-life. So they'll take a radioactive sample, they'll put this through, and then they'll take the sample again, and then they'll see how the mass to charge ratio has changed over the course of 24 hours, for example, and then they can calculate half-life from this. Types of relative atomic mass calculation. So you can often be asked either to calculate the percentage abundance or unit abundance. I'll show you how to do this with a practice question. So relative atomic mass of boron from this mass spectra. So what you're doing is you've been given the fact that there is boron 11, and there's about 75% of boron 11, and about 20%. So it's about 80-20. So what you do is you do the number 0.8 times, so the percentage abundance as a decimal, so divide by 100, times by the mass, plus the other abundance times by the other mass, so 10. So that's 2, and this is 0.8. And so you get a relative atomic mass of 10.8. That's the best way to do it when you're just calculating it directly. But if relative abundances are not given as a percentage, you can then divide the total sum of your relative abundances instead of dividing by 100. So here they're given as percentages, which means that this question doesn't work. but each element has its own distinct mass spectra. A mass spectra with peaks at 35 and 37 is chlorine. Now, you've asked a good question, Peter. What about diatomic combinations such as Cl37 bonded with Cl35 or another compound of Cl35 and Cl35? They would all have their own peak on the mass spectra. No, you are absolutely correct. They would. So if you've got a sample of diatomic chlorine or elemental chlorine passed through, you would have a peak so you'd have a peak at 70. You would have a peak at when 35 and 37. So at 72, you'd have a peak at 74. And then you could also have peaks at 35 and 37 where they've decayed. So where it's split up into its constituent molecules. So it's really important to note that, because there has been, in many examples, there have been good questions where they've asked you about, in multiple choice questions, where they've asked you about to predict the number of mass spectra peaks based on, they give you an element and they say, okay, this is a and you have to spot that because it's a diatomic element, it can pair up in any way. So yes, there will be peaks that are relative. There will be peaks with more and peaks with less. Does that make sense? Peter? Okay. Yeah. So here we've got some elements of diatomic. So you'll have the peaks at 35, the peak at 37, but you'd also have the peak where chlorine has not split up. So a peak at 70, a peak at 72, and a peak at 74. And you would have to be able to identify that. Mass spectra can also help identify molecular samples, so compounds, because compounds can split up in different ways. Because once they become positively charged, they can split up into different constituent fragments. These different constituent fragments will have different fragments for each of these. And it's really important, especially when you're doing organic synthesis, a question that often comes up again at AS, and quite often at A2 as well in paper 2. You often will get questions about identifying particular fragmentation patterns from particular mass spectra. So you would need to be able to identify those. So that's kind of it. We're now going to talk quickly about electron configuration for the remaining 18 minutes of the session. If you have any questions about atomic spectra and atomic stuff, can you please let me know now? Okay, we've got a question from Jessica. Please, can you explain what fragmentation is again? So fragmentation, it's in the name. So a fragment is a breakdown product of something. When something becomes fragmented, you have a whole structure and then you've broken it apart. So fragmentation is when you've got a compound or a molecule and you put it through a mass spectra, it gains a proton. That gaining of a proton, or it becomes positively charged, will make that spectra, will make that compound unstable, which means it can break up and it can form different fragments. And these different fragments can correspond to different structures that are in the molecule. Does that make sense? And thank you. No worries. Is there a link to these slides from Ghazal? Unfortunately, I can't supply you the link to these slides. I've downloaded all of these slides for this lesson, so I wouldn't be able to share those with you. Are these videos on YouTube? Yes, they are. Nuseba. Yes, they are. They are available on YouTube, and they'll be available on YouTube as we go forward. And all lessons, both biology and chemistry. So remember, biology on Fridays, chemistry on Sundays, all of them will be available on YouTube to either live watch. But I would still recommend coming because I can answer any of your questions that you might have. Electron configuration. So electron shells, subshells, electron notations, electron configuration, periodic table, and ionization energies. We're going to talk quite a lot about this now. So in GCSE, you were taught this 2882 structure, and we're going to break that down even further. So electrons move in shells around the central nucleus. The shells represent different energy levels. But within those shells, they can break down into different subshells. So the fixed energy of an electron is the amount of energy needed to move electrons from one energy level to another energy level. The energy level of electron shells increases as distance from the nucleus increases. An electron shell that is further from the nucleus has a higher energy level. That kind of makes sense. So the electrons at different points are at higher energy. The principal quantum number is defined as the number given to each electron shell. So N1, shell 1, shell 2, shell 3. So the principal quantum number is the shell number itself. A subshell is an orbital within a shell which has the same energy levels. So they're different orbitals within a shell that share the same energy levels. A good question here from Ashar. Can electrons be seen in an atomic force microscope? No, electrons are too small to be seen by microscopy alone. Electron shells, and Aaron, are there going to be A2 topics covered in future lessons as well? Yes, there will be. Majority of the A2 lessons will be covered closer to your exam time, so after Christmas. My idea is hopefully to finish AS content before Christmas now, and then A2 after Christmas, and hopefully that proves helpful for both AS and A2 students. Electron shells are divided into subshells, which each have a different energy level. There are 4 subshells, S, P, D, F. Some people do fencing. So shell 1 only has one subshell, one S subshell. So the electrons all have the same energy level. So shell 2 has S and P subshells. Shell 3 has S, P, and D subshells. So it is a bit different. But the best way to do this is to think of shells as different energy levels on a staircase. So if you imagine, I don't know if anyone has ever seen this. Let me know if you have seen this before. So the order of filling shells, the best way to go is you start with 1s, then you go to 2s, you again go to 2p, 3s, and then 3p, 4s, 3d, 4p, 5s, and then that would be the logical kind of ordering of it. So think of that as the energy levels in the stairs, and that's the best way to imagine it. The lower the energy of a subshell, the closer it will be to the nucleus. In shell 3, the 3s subshell has the lowest energy in shell 3 because it contains electrons that are closest to the nucleus. The 3d subshell has the highest energy in shell D because it contains electrons that are furthest from the nucleus. You can see increasing energy as you go through. Now, there is an exception to the general rule of you having to fill the 3 shell before the 4 shell. And I'm sure you'll, Peter, you noticed it. 4s and 3d are on the same level. But what happens is the 4s subshell fills up first. Once the 4s subshell fills up, however, it then goes to a higher level than the 3D subshell. And the 3D subshell goes to a 3D subshell goes to a lower energy level, where then it is able to become filled up. So it almost like they switch around. So 4S fills up first, but 3D then is able to, it fills up, it moves to its higher energy level, 3D comes down and it takes the extra electrons in. So the exception is the subshell 3D has a higher energy level than subshell 4s, but 4s fills up first. Each subshell can hold a specific number of electrons, and these electrons are held in orbitals, and orbitals hold 2 electrons. So S subshells have 1 orbital, so can hold 2 electrons. F subshells have 7 orbitals, so can hold 14 electrons. Question from Mariam. Does an electron have more kinetic energy in a higher energy level? It's not necessarily about the kinetic energy. It's to do with a mixture of the kinetic energy and the force of attraction to the nucleus. So yes, at a higher energy level, there is more kinetic energy in the electrons is spinning. It is orbiting at a different rate, but it is also to do with the fact that you have less attraction to the nucleus. Because so the nucleus is a restricting movement. The further you are away from the nucleus, the easier it becomes to move. So as you can see, this is kind of your general structure. So the number of orbitals increases by 2 each time, and the number of electrons increases by 4 each time. Zach, so if the 4s subshell fills up before 3d, does 3d subshell empty before 4s? Good question. It does, yeah. So 3d subshell, in transition metals, which are the ones, so in partially filled 3d subshells, yes, but there are exceptions to the rule. Again, something you come across in the transition metals topic in A2, you'll end up realizing that there are exceptions to this rule, and there are ways that this does change. But I won't go into too much detail about it now. I'll go into more detail about it when we do transition metals. If the 3D subshell isn't completely full, how would I write this? You would basically write it the same way you would write anything. So 1s, 2, 2. Like that. Like copper and chromium. Yeah, copper and chromium are exceptions to the rule. We will talk about this in more detail when we get around to A2. So each shell can hold a specific number of electrons, and we've kind of talked about this in a lot more detail. We've repeated ourselves quite a lot on this, but an orbital is a volume of space where an electron is most likely to be found. Each orbital contains a maximum of 2 electrons. These electrons spin in opposite directions. Crucial bit of understanding when you're talking about electronegativity. It's something called, can't remember the rule, the name of the rule, but basically, remember, electrons in orbitals are going to repel. So for a p subshell, it's going to fill an upspin orbital in all of, it's going to fill its upspin electron in its orbitals first, and then it's going to fill its downspin electrons. This is really becomes really relevant this becomes really relevant when we're talking about electronegativity, because it's something that we talk about in a lot more depth when we're talking about sort of why there are dips in electronegativity, specifically between group 5 and group 6. There's a dip, and it's because of this. But again, we'll talk about this in more detail at that point, but you do need to recall that. So in each orbital, one spins up and one spins down, and orbitals within each subshell have the same energy level. So subshell notation. So you start by noting energy level, then the type of orbital, and the number of electrons in that orbital. Each box is equal to 1 orbital. Arrows inside the box is an electron, and they always point in opposite directions to indicate they're spinning in orbits, opposite directions. And remember, they fill, so the 3s subshell fills before the 3d subshell, and in 4s is written before the 3d, unless both the 4s and the 3d are full. It's called Hund's law. Thank you, Vuti, for explaining that. That rule about filling up your upspin electrons first is first before spinning your downspin electrons is Hund's law. So as you can see, calcium, you can see how you're filling. And then after calcium, it then changes up. Electrons fill each orbital in each shell. Electrons fill each orbital in each shell individually. When we fill orbitals in a particular subshell, we try to avoid having pairs of orbitals because 2 electrons in a single orbital requires more energy because there's a natural repulsion between the electrons. So in the 2p, you're trying to fill up first before down. And that's called Hund's law. And remember, ions, to find the electron configuration of ions from either the s or p block, the electrons are eliminated from or added to the subshell with the highest energy. So take the electron configuration and then add or remove electrons from the subshell with the highest energy. And remember, the limit to that is the limit of the number of electrons that could fill up in that subshell. So you can't get any more than Cl minus. You're very difficult to get Cl2 minus or Cl3 minus because you'd have to add a new subshell in, which doesn't want to do that. So calcium forms a positive ion, so Ca2 plus, which means 2 electrons would be removed from the 4s subshell. It's very difficult to remove 3 electrons from the 4s subshell because you're not removing any more than the maximum subshell point that you're at. Fluorine forms a negative ion, so that means an electron is added to the highest energy subshell. So Fl minus, you're just adding an electron to the p subshell. In some textbooks, this goes back to the question that someone asked earlier. Do exam boards accept Ar when electron configuration has a higher atomic number than argon? You can do that. It's a shorthand method. If they ask you to write out the full electron configuration, write it out in full. If they don't, and if you're giving it as an explanation of your answer, you're welcome to write the shorthand method. Rules about transition metals. So just to end with, I was asked by Audrey to talk about copper and chromium. So the expected configuration, we would expect a configuration of 4s2 3d4 for chromium, but instead we get 4s1 3d5. Why is that? Because it's more stable to fill an electron in every orbital than it is to have repulsion within the s subshell. So it is more stable to fill an electron in every orbital than it is to have repulsion in the d subshell. Copper, similar principle. It is more stable to have a full d subshell than it is to have both electrons in the s subshell. Yeah, because there is one electron in each orbital. And yes, these exceptions are in the spec. You'll learn that in A2 mainly, but it is a bit of an A2 topic. It's in all the specs. And remember, when forming ions, they lose their 4s electrons before their 3d electrons. So Cr3 plus is going to lose its electrons from 4s before it loses its electrons from 3d. The electron structure then defines an element's chemical properties. Electrons are transferred when atoms react to form ions. Elements in the same group are very similar. They have the same number of outer electrons and therefore have very similar chemical properties. We know that because it's the same number of shells, same number of electrons in their outer shells, which means that they can lose and gain the same number of electrons to form ions. No, you can't just write for argon as Ar in brackets because that would be a bit of a cop-out, which they wouldn't let you do in the exam. And you know your S block, your D block, your P block, and your S block as well. We're gonna stop here. I'm gonna for this bit of the lesson. I will host a catch-up on atomic structure and a little bit more on electron structure in a future lesson because we haven't been able to finish everything. But I'm opening up to any questions.